In this segment, we're going to talk about characterizing variability. Does frequency and location of those samples make a difference in prescription development? In this example, we'll talk about a field that's located in Kentucky. It's 67 acres. It's 45 acres of bottom ground, 22 on a hill slope. It has 4 predominant soil types, a Kennebec silt loam, a silty clay loam, another silty clay loam, and then a silt loam. So we divided it up into zones, the bottom ground, the side slope, and the uplands. We can also grid sample this field. So if we look here, we have a 2.5 acre grid with many sample points, a 5 acre grid, and a 10 acre grid. To make a phosphorus prescription map for this field, I've applied the Nebraska soil phosphorus recommendations. The soil data is interpolated by Kriging, and the prescription is based on the University of Nebraska-Lincoln recommendations, where if soil P is less than 25 ppm, then the phosphorus rate is 25 minus the soil test times 4. If the soil phosphorus is over 25, then the P rate is 0. So there's a couple different interpolation methods. I mentioned that we use Kriging. The other one that is commonly available is inverse distance weighting. These are commonly available in most software packages that you will use to interpolate and map out your soil test data. So first, I'm going to show a prescription map for phosphorus based on that zone sampling strategy, where we broke it up into uplands, the side slope, and the lowlands. And as we can see in this example, there's a small area here that is different from all the rest. And this area here is where there's no phosphorus, and the red is going to be applied. And then we have a small area that needs an application based on the zone sampling strategy. Now in this example, instead of combining all those soil samples into one bag for those zones, we took and combined the samples by a 10 acre grid. And then we interpolated those grids. And now all of a sudden we see a much larger area that needs phosphorus application. Next, I did 5 acre grids. Again, combining soil samples into more bags, so more intensive soil sampling, more expense, but we see a much larger area that needs a phosphorus application, and we've kind of restricted this red area that gets a 0 rate to a very small area. And lastly, the 2.5 acre grid, which is more standard in the industry, is really going to apply more phosphorus across the field. So what we ended up seeing in this example was that, first of all, we weren't cutting back our phosphorus application by breaking the field up into smaller areas. If we look at the total amount of phosphorus that was applied, we're applying the most with the 2.5 acre grid. If we had done a flat rate and combined all the soil samples taken in that field into one sample and sent it off to the lab, the recommendation would have been for 0 pounds per acre of phosphate. So in this situation, we probably would gain some yield advantage by using an intensive grid sampling. This isn't always the case. In conclusion, high-resolution grids are required to make meaningful decisions. In this example, landscape features did not explain variability, so the grid sample was necessary to pick out the high phosphorus and low phosphorus areas. Precision sampling can result in yield increases, but this is not usual. And we again have to consider that current P&K recommendations might not be precise enough to support this level of precision soil sampling.